At the other end, it is very, very similar in nature, except that it is going to happen in the reverse. In data de-encapsulation, which some people refer to as unencapsulation, the bits themselves are received at the physical layer on the network medium. What happens at first is that every system on the wire will actually view the layer 2 header to see if the MAC address matches their own. If the MAC address does match their own, then it indicates that the packet is in fact for them. However, any host that does not match the local layer 2 header will discard this frame and will not examine it any further. Once the layer 2 header is verified by the receiver, indicating that this data packet was in fact destined for this particular receiver, the receiver will actually perform its own check of the information from the layer 2 header all the way through the user data using the same type of mathematical computation, which is media specific. It will come up with its own answer. We'll then look into the frame check sequence field and figure out what answer the sender actually identified originally. If the two answers match, it indicates that the frame was received correctly, and thus the frame check sequence has actually served its purpose. The frame check sequence is sometimes referred to as the CRC, or cyclic redundancy check. Once layer 2 has been verified, the remaining data would be passed up with the layer 2 header stripped off. At this point, the network layer is going to identify any layer 3 information, such as the source and destination addresses. Verifying this information, it will strip off the layer 3 header and pass the remaining data to layer 4. Now at layer 4, which is the transport layer, we typically have something like a port or a value, which is used to send the data to the right application. Any information which needs to be executed at this point can be executed, and the remaining data would then be passed up to the appropriate session level and application level component. Here at layer 5, session level information is stripped off. Layer 6 information is applied and then stripped off, finally leaving us with nothing but the application layer data, where authentication or synchronization of peers may have occurred. Once layer 7 has its job done, then plain user data is passed up to the physical application or the actual application. Now there are a couple of points about data encapsulation and data de-encapsulation that are very important. Not everything that a sender and receiver will do happen inside of a single packet. So we will see that every one of our layers is required. Certain things will happen in certain times. Let's say that an application requires authentication before any data can be sent. Authentication has to happen at layer 7, thus everything else that occurs below layer 7 is all based upon supporting this authentication routine. So when the sender will actually send the data from layer 7 during the data encapsulation process, the layer 7 component will perform authentication. Everything below it is going to be in support of that authentication request. Thus, when the data is received during the de-encapsulation process, anything that is stripped off down below is fully in support of that authentication itself. In fact, when systems are communicating with each other, they both must be utilizing the exact same protocols and information on both sides so that the processes that happened at the functional layers of the OSI model can actually do their job. This is what is known as peer-to-peer communications. Peer-to-peer communications is actually the process of one sender being able to communicate with a receiver. Now, of course, this can be multiplied many, many thousands of times on the same network. But the fact is that every sender and every receiver that exist in a conversation have to have the same protocol and the same settings for their network to be able to get it to work. When the network stack itself is doing its job, different layers of the OSI model that are being emulated by the network operating system are going to have different protocol data units for each and every layer. For instance, things that happen at the session layer or above are known as true datagrams. A datagram for an application is required for an application to do its job, whereas peer network communications begin to occur at the transport layer itself, where segments are physically sent from the transport layer directly to the transport layer at the other end. Segments typically indicate anything required for guaranteed delivery of packets and to provide acknowledgments when data is in fact received. The network layer is where our packets are actually formulated. Packets are going to be routed through the network environment, and the protocol data unit, or PDU, which occurs at layer 3, is known as the packet. Once we drop down into the layer 2, we have now built a frame. So when we are dealing with elements of layer 2, we're typically talking about frames. And then, of course, below the physical layers, we are always dealing with bits. The very important thing about all this is that every layer of the OSI model is designed to functionally provide some support for the communication of applications across the network. Whether it is something that has to happen at layer 4, where we are dealing with segments, or something that has to happen at layer 3, where we're dealing with packets and packet-based information. It doesn't really matter because every single host in the network has got to support the OSI model, the same protocol, and the same configuration for any of this to work together. Now it's time to begin our learning of the TCP/IP protocol. This is one of the most important protocol suites that we utilize on our network, and it's essential that we understand its history and how it is utilized and how it actually works at a low level. So we want to begin looking at it from a high-level perspective and then dive deeper into its relationships to the OSI model and all of the things that it does to allow us to communicate on the internet and our local network. What's amazing is that the idea for the internet and TCP/IP actually began more than 35 years ago with the Department of Defense. Department of Defense actually had a project that they were actively pursuing, which was designed to interconnect all of their islands of automation, the different mainframe computer systems that they had from different vendors, and which did not have any common connectivity between them. The idea was what's known as the ARPANET, or DoD ARPANET, the DARPANET. This stands for the Advanced Research Projects Agency Network. This network was actually set up and designed to interconnect the islands of automation at key strategic locations by creating what are known as alternate communication routes. TCP/IP research actually began through funding by the Department of Defense and through Stanford University, which actually developed the original DoD model, or the 4-layer TCP/IP model that we know today. The protocol system then evolved and became the protocol choice for use in the ARPANET, or DARPANET as it's referred to. We also began to see the National Science Foundation, NSF, take hold of this protocol, and based upon the ARPANET standard, it actually created or evolved it into the internet as we know it today. So all of this began back in 1969 when this first research towards consolidating this type of difference in network connectivity started, and that's really where TCP/IP came from. Now, TCP/IP is the primary protocol for the internet, and it has just simply grown by leaps and bounds in popularity. In fact, its popularity is based upon the ability for it to be routed over large networks and to be used by virtually everyone on the planet. It has a large number of built-in utilities, applications, tools, and capabilities, and is required for connectivity to the internet. More than 98.5% of all corporate bandwidth in the world utilizes TCP/IP protocol transmissions, which means that it is something that we definitely need to know. One of the biggest problems that we have with TCP/IP at this time is a depletion of addresses, public addresses. And thus we're starting to see a new version of TCP/IP being invented and implemented. Right now, IP version 4 is what we're currently using in most implementations. But we will soon be seeing IP version 6 being used, and we're already beginning to see it somewhat in much of our computing environments. Let's start off by looking at IP version 4 and kind of map it to information that we already have about the OSI model. Mapping the TCP/IP model to the OSI includes what is known as the DoD, or TCP/IP 4-layer model. This 4-layer model includes the process application area, where all applications that run in the TCP/IP protocol suite actually encompass layers 5 through 7. The host-to-host layer, as it's known in the original DoD model, is the functional equivalent of the transport layer. There are 2 protocols that exist at layer 4, in this case at the host-to-host layer, the TCP protocol, or Transmission Control Protocol, and the UDP, or User Datagram Protocol. These 2 transports will give us an option of either connectionless transmission or connection-oriented transmission. Now, the idea here is that connectionless transmission can be sent best effort delivery with no acknowledgement of data receipt, whereas connection-oriented transmission is actually an established connection or session between 2 systems where all data that is sent from one system to the other is going to be acknowledged upon receipt. This guarantees the delivery, and that's why it's called a guarantee acknowledgement type of protocol. This allows us to use applications that have a higher level of criticality and to use them with a lot more confidence. At the internet layer, which is the functional equivalent of layer 3 of the OSI model, we see the primary protocol in the TCP/IP suite, which is known as the IP or Internet Protocol. The IP protocol's job is to handle all of the routing, the addressing, and all the functional aspects of TCP/IP conversations. It utilizes 3 different main protocols to assist in its communications: ICMP, or Internet Control Message or Messaging Protocol. And this is a protocol that is used by the IP protocol for assistance with TCP/IP conversations. The ICMP protocol is also used for testing via what is known as ping, or Packet Internet Groper, which gives us the ability to identify if a target system is alive or on and connected to the network. In addition, at layer 3 of the OSI model and on the internet layer of the TCP/IP DoD model, we must have a protocol that allows us to map the native IP addressing, which is used by the IP protocol, to map to the burned-in address, BIA, the MAC address of the target systems. What we use here is the Address Resolution Protocol and the Reverse Address Resolution Protocol. Address Resolution Protocol, or ARP as it's known, is responsible for mapping IP addresses to layer 2 MAC addresses, whereas the Reverse Address Resolution Protocol, or RARP, is responsible for mapping a layer 2 MAC address to a layer 3 IP address. So one uses forward addressing and the other uses reverse addressing, and thus it is called the Reverse Address Resolution Protocol, or RARP. However, the 3 main protocols of the TCP/IP protocol suite are IP, UDP, and TCP. It is very important that we understand the characteristics of each one of these in greater detail. So we've learned about the fundamentals of the OSI model and the basics of TCP/IP. We've also learned how the TCP/IP protocol suite relates to the OSI model. This is all very important as a foundation for you as you begin to learn about the in-depth knowledge in how TCP/IP actually works on a network. That'll be the next step. As we begin to dig deeper into the TCP/IP protocol, we'll need to understand some of the fundamental protocols used in this suite. This includes, of course, TCP, the Transmission Control Protocol, and UDP, as well as ICMP and others. So we'll begin looking at those now. The first protocol, the Internet Protocol, has specific characteristics that you need to be familiar with. Obviously, working at the network layer of the OSI is one of its most important features. It handles all activities at layer 3, the logical addressing, path determination, being able to route packets properly, and so forth. It is connectionless and does not have any capabilities for data recovery. It actually relies upon upper layer protocols for this functionality. Packets are always treated independently as well. By IP standard, it has no capability or intelligence to identify a full session level activity. So each packet is treated as an individual conversation. Moreover, the Internet Protocol does not have the same types of advantages that the TCP protocol does. The TCP protocol can actually establish a session and has no connection limitations. IP also implements a hierarchical addressing scheme, giving us the ability to address as many systems as would be required in a hierarchical fashion. This makes it easier to understand and administer once we decide exactly what the addressing schemes look like. One of the things that we're going to explore in greater detail in this course is to understand how these addresses actually look and how they're going to be applied to our networks and our hosts to make IP function. In addition, IP uses a best effort delivery, very much like UDP. It does not require an acknowledgement for packets that are sent. It relies upon an upper layer protocol to do this. It also does not have any data recovery features. You'll actually find that the Internet Protocol, or IP protocol, is very much the same in basic function as UDP.